if you're going to use these in an array, the best thing to do is to buy them from a manufacturer that does that for you, and there's the manufacturer. It's hard to do this yourself. Not impossible, but if you're going to build your own high impedance amplifiers, you need to put them on a lab bench and verify they have the same gain, the same phase shift before you put them in your array. So most of us will probably buy them. Yes?
All that stuff's good, but I got land that is the same elevation. I got tons of land, but everything is all over. So
how much? How much difference in the? Well, yeah, you wouldn't want to put 4 phased verticals with the verticals separated in height by more than, let's say, 5 or 10 feet. So you'd have to find some flat space. Maybe you need to find a bulldozer to take some of those hills and put them in the valleys. No, it doesn't have to be precise. I'll show you my antenna a little bit later. But you don't want it to be crazy either. I'm afraid having 2 verticals 100 feet different elevation wouldn't perform properly. Maybe you need one of those 3-foot diameter loops. So here's the high Z array. Does anybody here have one? Quite a few. So tell us what you think about it. Just briefly. John, what do you think about yours? And what's the spacing between the elements in yours? 80 feet. Yeah, I think it's a good compromise between 160 and 80. Which band is it best on? Yeah, we use it only on. And what about anyone else have a high Z over in the back, the extreme back of the room? And what's the spacing between the elements? 50-foot spacing. Yeah, 50-foot spacing is a little too tight for 160. Yeah. Okay, and the fellow in the extreme back of the room. Okay. Okay. So anyway, there's some experience. There's a lot of high Z arrays out there, and I think generally the results are quite good. There's an alternative. And for people that like to build their own antennas like me, this is a fabulous alternative. But there are some trade-offs. This does require radials. And the reason it requires radials is not to get the loss down. Remember, we're dealing with 45-degree noise figures here. So I don't care about loss. And the radials aren't going to reduce the angle of radiation for this antenna. It's the only reason you need radials is to stabilize the feed point impedance of the antenna so that it doesn't vary wildly. And my situation is kind of a worst case where my antenna is, some of the elements are in a marsh. Some of the elements are a little bit higher elevation where it's usually dry. So the 8 different elements of my array, as the weather changes, they have quite varying impedance, particularly the ones in the marsh. That marsh sometimes dries out. So I found, in my case, that with 8 radials, 70 feet long, that the feed point impedance stays pretty constant, within about 20%. I've measured it a few times when it's dry and wet. And it turns out, since my array has wide spacing, quarter wavelength between the end fire elements and 5/8 of a wavelength between the broadside elements, that the array design is relatively insensitive to amplitude errors. So you don't have to have perfection here. If you're using low impedance verticals in a compact array, the sensitivity to amplitude errors is greater, so you might need more radials. I've never attempted to build a small 4-square with 4 passive verticals, but I know you can do it, but depending on your conditions, you might need some more radials to stabilize it. It's completely adequate to just lay these radials on the ground. They don't need to be tight. And in fact, if they're laid on the ground, the safest way to do it is just to lay them loosely on the ground, so that if animals go through the area, that they're not going to trip over it. If human beings are going over the area, that you're not going to trip over it. So I just lay my radials loosely on the ground. And at the end of the season, when I go out and I have to take my array and put it away for the summer, it's in an area that has to be mowed. Those radials are really randomly scattered all around, but I can't tell any difference in the performance of the antenna. Doesn't seem to matter. As long as the feed point impedance is stable enough, it's fine. This antenna, the one I built, also has 4 25-foot umbrella wires. And you can see W5ZN has a really good website that talks about this, w5zn.org. That's just a mechanism for increasing the apparent length of the vertical. If umbrella wires are a problem, you could use 4 35-foot verticals with no umbrella wires. You could use as little as 65-foot spacing in a compact 4-square array. No amplifiers are needed. This antenna produces about the same signal level as a beverage, so you don't need amplifiers at the base of the antenna. So there's no need for precision matched amplifiers with accurate gain among the different amplifiers in the array and accurate phase delay. It's very tolerant of nearby objects. It's a low impedance antenna. You could literally put one of these in a tree if you needed to, and it wouldn't matter. And it's very, very easy to build. And for the larger arrays with quarter wave spacing, the arrays are very tolerant of moderate errors. So this is for anybody that's built a Yagi. You know, a Yagi just wants to work. It's hard to build a Yagi that doesn't work. It's hard to build this antenna and have it not work also. It just wants to work. The physical dimensions, the spacings, are what really makes this thing work. And here's a photograph of an antenna like this, low impedance 4-square. Here's a website for the guy that built this thing. Very easy to build. The 4-square has about 100-degree beam width, just like a full-size transmitting 4-square. Its performance on receiving is every bit as good as a 4-square with 125-foot tall elements. And the RDF of this small antenna, 65 feet on its side, is actually better. It's slightly better than the RDF of a 4-square vertical, 125 feet on its side. About a dB better. The side lobes are lower. But because it's small, you have to worry more about the stability of the feed point impedance. So you might need more radials, particularly if you're in an extreme case like mine, where some elements are in a swamp and some elements are on dry land. This very, very easy antenna to build. Okay, so let's go look at some larger antennas. Yes, this is a single frequency antenna. But John, the honest truth is that even for the high impedance antennas, like the high Z, where you can use those on more than one band, you can only optimize them on one band. They're really excellent receiving performance, even with the high Z arrays. If you optimize them for one band, the performance is actually quite poor on the other bands. So what some people do is they set them for a compromise, so they work pretty well on 160 and pretty well on 80. But you can't have your cake and eat it too with either array. So yes, there's no question that the low impedance antenna is definitely a monoband antenna. There's no way to make a compromise with these and get them to work on two bands. But likewise, for the high impedance antenna, if you want to optimize on one band, then they're quite poor on another band. Okay, just one question. Your name and call sign, please. You're talking about the low impedance array? Yeah, the low impedance array, you actually, let me go back to the verticals. You actually resonate this antenna. And if you go to the W5ZN's website, w5zn.org, he'll show you how to do it. It requires an inductor on 160 meters. It's about 28 microhenries. A receiving rating inductor. It's about the size of your thumbnail. And the way you match the low feed point resistance of this antenna, the feed point impedance, is dominated by the lossy radials, because you only have 8 radials. So if you had a perfect radial system, the feed point impedance would be a couple of ohms. But we want loss. We want loss to get rid of the mutual impedance between the elements. So we want loss, so we have the lossiest radial system we can have without too much variability in the radial system. So the direct feed point impedance is about 20 ohms because the radial system is so lossy. With these arrays, you use 75 ohm RG6. So you put, how do you match 20 ohms to 75 ohms? Use a resistor. Loss is our friend in these arrays. We want loss. If we didn't care about the stability of the ground resistance, we would have an even worse radial system because we want loss. If you were to build this antenna on a desert, you'd probably have a very sparse radial system because you wouldn't have much variability. But most of us would build this with 8 radials, a 28 microhenry receiving choke, cost about 75 cents, and a 50 ohm resistor. That's how we match it. And you tune the exact value of the inductor for resonance at 1830. And in fact, what I do is I actually trim the length of my umbrella wires instead of varying the inductance. It's so close anyway, I just trim these umbrella wires, and I think they actually wound up being 24 feet resonant at 1830. By the way, dimensions are big enough, you could build a 160 meter foursquare of low resistance, low impedance verticals, and you could place the 80 meter foursquare inside of it. There's enough space to do that. And the mutual coupling is so low between these verticals that have all this resistance from the lossy radial system and the 50 ohm resistor in series that the mutual impedance between the elements is negligible. So you can nest the verticals inside each other. Okay, so yeah, we can make it bigger. You can buy this array. It's optimized for 160 meters. It's a high impedance array. You can buy the whole thing. DX Engineering will take your credit card this afternoon. You'll have it all. No umbrella wires, no radials, precise matched amplifiers. He came up with a very clever way to reduce the size of this array to 200-foot diameter. Very unusual. It was done experimentally. Believe it or not, the phase relationship among the elements is 107 degrees. Rather odd number. You can read all about it right here. The RDF of this antenna is quite remarkable, and it takes about an acre. Not bad for 1 acre compared to 20 acres. You can do the same thing with low impedance verticals. Very nice if you want to build your own antenna. This is my low impedance vertical. And I'll just tell you a little bit about how I built it. 25 feet of aluminum tubing, 4 25-foot top hat wires. The length of those wires is trimmed to set the feed point to 0 reactance at 1830, set it to resonance at 1830. Right here is a little box that the receiving inductor and the resistor are located in. The ends of the top hat wires don't go down to the ground because I have lots of deer, so they're fastened through a short rope to the top of a 6-foot fence post, so it's high enough to keep the deer out of it. If I attach these top hat wires to a stake in the ground, they wouldn't be there after one night. But that's a real easy solution, and this is a simple enough thing. These are only up in my place 6 months out of the year, and I can install this vertical in about 1 hour. So it takes me about a day to put up these 8 verticals for the array. So that's not bad. Okay, we're getting to the last couple of slides here. These guys are happy to see your credit card. This is a marvelous device. It's really quite amazing. It's not inexpensive. But what it allows you to do is to take any 2 receiving antennas you might have. On 160 meters, they should be vertically polarized. Bring those receiving antennas in here and you can use this to steer a null. So if you have, let's say, the Big D expedition to Crozet Island is coming up next year, and the night before the D expedition, a noise source pops up, and you can't hear the weak signals because of it. Well, if you have something like this, you can take two vertical antennas or two beverages and steer a null right onto that noise source and get rid of it. So this is a handy device to have. This is also for a bidirectional beverage. This is a better way to configure a bidirectional beverage. Bring both signals from both directions on the beverage into this box, and you can steer the null around the back. And the last slide, the other marvelous thing you can do with receiving antennas is to use them for diversity receiving. And to the best of my knowledge, the only device you can buy to do this is the Elecraft K3. And it is just amazing to listen to. Both receivers are full performance receivers, fully phase locked, and the impression you get in listening to this receiver on two widely spaced receiving antennas is that the position of the signal in your head is moving around from left ear to right ear to the middle, and that's the impression you have, and you sense that movement all the time. Okay, that's the end of the presentation, and I have time for a couple of questions if any of you have any questions. Right here. I can't imagine any advantage to doing so. I think the answer is no. You're just making it more complicated. All you need is a single wire. There's no reason to make it more complicated that I can think of right now. Maybe later I'll think of a reason. But believe me, if I had thought of a reason, I would have done it. The vertical is just as simple as 25 feet of aluminum tubing or copper tubing or a piece of wire on a bamboo pole or anything you've got. Just keep it as simple as possible. Yes?
Dave, NANB. I have a Burnell on 160 and I'm still going to get the small loop for receiving. Would diversity reception be good?
So you're thinking about that, or well, remember this: the so-called magnetic loop is a very, very specialized antenna. It only has one use in life, and that is to get rid of a nearby single RF source or RFI source. So I wouldn't choose to use this antenna for the purpose you just described. If you want to do what you described, I would go to one of these that provides useful directivity for skywave signals. And as you saw, for example, the K9AY loop, it only requires a 25 by 25 foot area. But let me mention one other thing about diversity, since I brought that up. Notice, in order to get useful diversity reception on 160 meters, you need wide spacing. It isn't useful for diversity reception to take two verticals that are located a few hundred feet apart and expect miracles to happen. It won't happen. You need space. Any other questions? John? Yes. Well, my first comment is that I thought about that and chose not to do it. For a number of reasons. Probably in my mind, most important is that I have to install my array every October and remove it every April. So that was more complicated than I wanted to do. But my opinion is that when I've modeled loop antennas, they all have what I would call undesired high angle response. So although I have never built or modeled a large array of loops, my feeling is that the relatively high RDF of a single vertical is an advantage compared to a loop. It has A single vertical has very low response to signals coming in at high angles. So I think simple is good. So any other? I'll take one more question and then we'll move on. Yes. I think somebody in the room who's tried that might be better, because I've never done it. Actually, we do have time for more questions. The next presentation begins at 10:15, so we can keep going. Who's tried it? Yeah, and that, by the way, is also an advantage of the low impedance elements, because they don't have these high gain amplifiers, so you don't have that problem. The low Z verticals are very immune to problems in a multi-transmitter environment. But as Craig mentioned, you can eliminate the problem in the high Z antennas with filters, and with the low Z verticals, you don't have the problem. It just doesn't exist. Any other questions? Yes, right in front. Name and call sign, please. Yeah. Yes. All dimensions of the presentation are for 160. Yes, that's correct. So it's a very good question, Rob, because I've tended to focus on 160. I only had an hour for this presentation. And for most of us, 160 is a place where we really need receiving antennas, where the payoff is really large. But these same antennas that I've described here are also very effective on 80 and 40 meters. These high RDF numbers are only obtained, regardless of what manufacturers' literature might say, these high RDF numbers are only obtained with antennas that are designed for monoband use. The high RDFs are all of these arrays, and they're optimized for a single band. Yes, you can build a compromised version of them, but they are compromised. So the RDF goes down, and you get compromised performance on more than one band. But if you want the really high RDF numbers, all of the phasing lines and the other things are cut for a single band. Jim.
Yeah, Jim, K9YC. Talk about, if you would, the interaction of these various systems with transmit antennas on the same band.
Very good question. Okay. Thank you for asking that question. It's all about RDF. So let's see if I can find the beginning of. Oh, here's the website, by the way. I referred to this website. It is w5zn.org. This website has construction level details about how to build a low impedance array, and I recommend it highly. The developer of this large 8-circle array is WHAI. It was his original concept more than 10 years ago, but it's really gotten to, as more and more people have used them and said, wow, this is like a 5-element Yagi on 160, they've become more and more popular for people that have a few acres for them. But let's take a look at these RDF numbers, okay? The higher you go up this scale of goodness, so as the really good RDF numbers are characterized by antennas that have a narrow main lobe and all the side lobes well controlled and low numbers, just like a really high performance Yagi. Well, just like a high performance Yagi, if you put other antennas really close to it, the performance of that Yagi degrades. And the same is true here. If you take one of these high RDF antennas, not so much the beverages, because they're quite immune to nearby, well, even re-radiation from towers is a problem with those. For the high RDF antennas, the RDF is ruined by nearby not only 160 meter antennas, but any other object that can pick up significant energy and re-radiate it into the antenna through its main lobe. So let's kind of pick a worst case example. You've built one of these 8-circle vertical arrays, but you only had space to put it next to a 130-foot tower. But that's not a problem. That's not a 160 meter antenna. That's a 130 foot tower for my 20 meter antenna. Well, bad news. Because what's going to happen is that tower, and I picked 130 feet, but any tower of any size at all, that tower is going to pick up 160 meter signals. It's just going to do it. And it's going to pick up 160 meter signals from all directions. And if that tower happens to be in the direction of the main lobe of this high performance receiving antenna, it's going to re-radiate signals from the back of the high performance antenna right into the main beam of the antenna. So if you want these kind of high RDF numbers, that array should be placed at least hundreds of feet, ideally many hundreds of feet away from tall towers. This is the last question right here.
My beverages that I'm going to be putting up this summer are two of them. They're 2-wire, but they're going to have to work for 80 and 160. So the 8 to 900 feet is probably great for 160. It seems like I got to compromise with that too long.
Yeah, it is. For excellent performance of a beverage, and a beverage is wonderful. It's a true multi-band antenna. Put up a 500 to 600 foot long beverage. It'll work very well on 160 and very well on 80, and you get RDF numbers of about 10 dB. Okay, that's it. If anybody has any other questions, I'll be around all weekend. You can reach me by email.